Hello, welcome to our team's Ultra Precision High Speed Slide. My name is Ezrin.
My name is Clay.
And my name is Stephen.
Today we are very excited to share with you the next step towards advancing modern manufacturing capabilities forward. Our group has taken the opportunity to work with Dr. Matt Davies, Oak Ridge National Laboratory, and UNCC's Dr. Chris Evans and the Center for Precision Metrology. In 2019, everyone on our team was in Dynamic Systems 2 with Dr. Davies. There was one day specifically we all remember where he talked about how Dr. Scott Smith, now at Oak Ridge National Lab, helped establish and develop high-speed machining. Since then, high-speed machining of monolithic parts has drastically changed the aerospace sector and manufacturing in general. This dynamic shift in industry was done with higher spindle speeds, larger acceleration capabilities of the machine tool axes, and overall faster velocity of the axes. Here at UNC Charlotte, Dr. Davies is heavily involved in ultra-precision machining of optics, specifically freeform optics. Along with Dr. Davies, Dr. Chris Evans at the Center for Precision Metrology is always developing novel metrology machines to investigate ways to make measurements at a more refined level. Oak Ridge National Lab is currently heavily involved in researching additive manufacturing, 3D printing for most, and specifically metal 3D printing. Oak Ridge National Lab, the Center for Precision Metrology, and Dr. Davies have all recognized that precision high-speed axes are required to push precision manufacturing and precision measuring to the next stages. Our solution to the current needs of manufacturing is a modular high-speed ultra-precision linear axis. Our target goals for this project are 2G acceleration capabilities, 10,000 millimeter a minute velocity, 300 millimeters of total travel, and sub 200 nanometer positional accuracy. Now we all know that a nanometer is 1/1000th of a meter, but to give you some perspective, a nanometer compared to a meter is the same as the diameter of a nickel compared to the diameter of the Earth. We are working in some very tight tolerance zones.
Current precision slides are big, slow, and heavy. 3D printers are fast, but not precise. We designed a slide that can be adapted to many applications such as diamond milling, coordinated axis turning, direct metal laser sintering, and all sorts of metrology applications.
Keeping our goals and project applications in mind, we began with a top-down approach. This approach first consisted of a literature review and a decision on the primary building blocks around which this project would be built. The basic building blocks for this project are a Renishaw displacement measurement interferometer, a Dover motion air bearing, and an Aerotech linear motor.
Integration of these selected components was a major challenge for the project. To mitigate design issues in the integration process, a positional error budget was created. The error budget allowed us to take note of any items that will induce error in the measurement performance. As the integration of the primary components evolved, the error budget was continuously updated to work toward achieving the positional accuracy goal.
From the basic building blocks of the system, some preliminary calculations are required to prove design feasibility. The first of these were how temperature, pressure, and humidity would affect the positional measurement. As these parameters change in the air, the index or the fraction of the air also, very slightly, changes. As the index changes, so did the wavelength of the source. The wavelength of the source is the measurement scale, so temperature, pressure, and humidity all affect the positional measurement reading. Edlund's equation was used to determine the magnitude of the effect on the positional measurement reading. It was determined using the error budget that a temperature change of 0.1 degrees Celsius, a 10 Pascal change in pressure, and a 10% change in relative humidity could all be withstood while maintaining the desired positional accuracy goal. To integrate all the components together, a frame was required. A kinematic mounting frame was designed around the methodology of constraining only the necessary degrees of freedom of the air-bearing rail and no more. 1 degree of freedom was minimally constrained in the kinematic mounting system to allow a differential thermal growth between the rail and the frame. The advantage of the kinematic mounting system for this project is threefold. Firstly, it does not distort or induce strain that can change system performance. Secondly, the position and orientation of the slide system is controllable and deterministic. Lastly, The kinematic mounting system allowed for much larger manufacturing tolerances than otherwise possible. The large manufacturing tolerances made it easy to machine the frame for the project on primarily the Haas TM1s available in the UNC Charlotte machine shop, along with some manual machines. Manual mills and lathes were primarily used in this senior design project for squaring to size. Sinker electro-discharge machining, EDM, and wire EDM was used to manufacture the spheres for the kinematic mounting features. As already stated, the Haas TM1 did the heavy lifting for the manufacturing of this senior design project. Mastercam 2019 was used to generate all of the CNC toolpaths and post the G-code.
Days before we were to begin our motor controls testing, COVID-19 applied the e-brake for Team UNCC slide. Therefore, no in-depth testing was completed to verify our slide's performance.
We, as a team, would like to thank specific UNC Charlotte faculty. Dr. Matthew Davies, Dr. Jimmy Miller, Dr. Christopher Evans, and Brian Dutter have all been a fantastic help for this project. We would also like to thank Tyler Blankenship for giving us constructive feedback as our grader. Lastly, a thank you to Nick Horvath at Oak Ridge National Laboratory for being a fantastic mentor, and the rest of the guys at RNL for giving us feedback during our presentations.